Hi, everybody. In today's lecture, I'm going to talk about the Michelson-Morley Interferometer. So, Michelson-Morley Interferometer. Now, in a previous lecture, I got kind of hand-wavy discussion of the Michelson-Morley Interferometer, so I'm not going to go into that kind of stuff today. What I'm going to do today is get into the nitty-gritty of it. So we're going to talk about how it worked, what the derivation looks like, and all that kind of stuff. So if you haven't already seen or watched the introductory lectures on Michelson-Morley, then you should go back and do that, because today what we're going to do is talk about the nuts and bolts. So here's kind of what the interferometer was like. We had a light source here on the left, and then the path of the light went then straight to a partially silvered beam splitter, okay? And then the beam splitters diverged the path of the light beam into two. And in one of those, it went to a mirror that I'm calling M1, and the other, it went to a mirror that I'm calling M2, okay? So what happened then is part of the beam went to M1 and then bounced and came back. And then part of the beam went to M2 and then bounced and came back. And then once it hit the beam splitter again, those two beams then would be turned and they would together go down to the detector, which is down here, which I sketched out as this little eye right here, okay? Now, we'll call the distance between the beam splitter and M1, we'll call that L1, and we'll call the distance between the beam splitter and mirror 2, we'll call that L2, okay? So the idea is that light comes in at the source, hits the beam splitter, goes to M1, bounces and comes back, hits the beam splitter again. And then, of course, simultaneously, the other beam is going through the beam splitter, hitting M2, coming back, and then the two traveling beams then merge together and go to the detector there. Now, because those two beams which took different paths, merged together, what happens is they create an interference pattern here. Okay, now to remind you, light waves can be in the same place at the same time. And if you have two light waves that line up crest to crest and trough to trough, that's constructive interference, right? And then where constructive interference occurs, there's going to be a bright light. So this turns into a bright pattern in the interference pattern. And then if there's a path beam difference in between, where, for example, perfect destructive interference is where the peak meets the trough like that, okay? This is destructive interference, okay? And then you would get dark, okay? So what happens is you'll get an interference pattern down here where the detector is at this eye, and then it'll create a pattern of fringes down there where the detector is. And then Michelson and Morley would detect shifts in this interference pattern. They could detect, they were very sensitive in their final device, and they could detect just a wavelength shift of 0.00, I think it was believed 0.005 shifts of the wavelength from right to left, and that would cause a shift of the interference pattern. Now, why was that important? So this is how interferometers work in general, but the Michelson-Morley experiment was testing the existence of the ether. And so the luminiferous ether is the medium that it was thought that light propagated through, which would serve as an absolute reference frame for everything, okay? Now, what they would do is they would orient their interferometer to be parallel and perpendicular to the path that Earth was taking through space in its orbit around the sun, okay? And then they could rotate their interferometer, so this whole thing rotates, right? We can rotate this guy. And you can rotate your interferometer so that alternatively, the path L1 was perpendicular or parallel to the luminiferous ether path. So let's call the drag of the ether. So if the Earth is traveling, for example, to the right through the ether, then the drag of the ether wind would be to the left. So I'm going to draw that as V here. And so this is the ether drag velocity. Okay, the ether drag would be left. In that case, then L2 would be parallel to V, the drag through the ether, and L1 would be perpendicular to V. And then in a separate experiment, I'll call that the prime experiment, they would rotate it. So this is experiment 1. They would then rotate it so that experiment 2 was the path of through the ether drag, okay? And then they compared the interference fringes for the drag in the different perpendicular directions. And that's how they created their null result of there is no ether drag kind of thing. That was the ultimate bit. So now we're going to get into the math of all that and the derivation of the equations that they did so that we can understand exactly how this thing worked. Okay, so what we're going to do is we're going to compare the time difference. So here's the point. We're going to compare delta t for V parallel to L2 with delta t for V parallel to L1, that position vector. So it's either along the M2 line there, the ether drag is, or it's along the M1 line there, okay? And we're going to compare those. And I'm going to call it when the ether drag is along the direction of L2, I'm going to call that delta t, and then I'm going to compare the time difference there for delta t prime for V parallel to L1. So we're going to compare those two things, okay? If we see no difference there, then that'll be Michelson and Morley's null result. In other words, if delta t and delta t prime are the same, then null result. Okay, and then that's what it means, no ether. And V is equal to 0. Okay, so that was kind of the point. All right, so let's look to talk about how much time it takes for the light to travel from the mirror to M2 and then back again. And then also let's compare that with the time that it would take the light to go from the beam splitter to M1 and back again. Because of course, these two paths, the one from the light to the beam splitter and from the beam splitter to the detector, those are going to be the same, right, for both paths of light. That's the same path, right? And so since they're traveling together there, we don't need to compare those things. We just need to compare the differing paths from the beam splitter to M1 and the beam splitter to M2 and see if those produce a different time of travel given the ether wind and compare that. Okay, that's what we're doing. So I'm going to talk about the amount of time that it takes the light to leave the beam splitter, go to M1 and come back. I'm going to call that the first time. And then I'm going to compare the amount of time that it takes to go from the beam splitter to M2 and come back, okay? And then we'll subtract those two, and that'll get us delta t, okay? And that should cause the interference fringes that are seen down here at the detector. Then we'll rotate the Michelson-Morley experiment, yet again, measure the time of travel from the splitter to M1 and back again, and compare that to the splitter to M2 and back again, and that'll give us our delta t2. Or delta t prime. Then we'll subtract those two things, and if those are tiny, tiny, or basically so small that it sets the ether speed as too low, then there is no ether. All right, so let's talk about what effect, under kind of classical ideas of relativity, the ether drag would have on light as it travels from the beam splitter to M2 and then back, okay? So in that case, what's going to happen is on its way from the splitter to M2, where the ether drag is this way, then what happens is on the way there, you have the light, of course, traveling at speed c, and on the way back, it's going to be traveling at c as well. But the measured speed of the light would be reduced by the ether drag as it goes from the splitter to M2, okay? So from splitter to M2, the speed would be c minus v, because the vector c and v point in opposite directions, and that would mean that the speed of light is slowed. Now, from M2 back to the splitter, we have c plus v, okay? because the speed of light in that case would be to the left, right? And that would add on to the v. Now, of course, this isn't what happens, and we know this now. We have special relativity now, but that's kind of what the idea was at the time. All right, so how much time would it take for something to go from the splitter to M2, which is how we have it here, okay? We called that distance L2. So how much time would it take for it to do that? Okay, so remember, speed is equal to distance divided by time. So if you want to find the time is the distance divided by the speed. So we would have two separate times because we have two separate speeds that we have to add to get T2. We'd have to find the time that it takes from the splitter to M2 at a speed of C minus V, and then of course from the mirror to the splitter again when the speed is C plus V. So that's going to be L2 over C minus V plus L2 over C plus V. And that would give the total time of travel for the light traveling along L2, which is parallel to the ether drag. Okay, so that's the first one. Now we can do a little bit of algebra here, if we'd like, and add these two together. So if we do that, we get L2 times C plus V plus L2 times C minus V all over the common denominator of C squared minus V squared, which would be, of course, C plus V times C minus V in the denominator. All right, that's what we've got. Now, when we solve that, T2 is then equal to, the V's cancel out, so the L2V minus L2V, that cancels out. So we end up with 2L2C over C squared minus V squared. So that's what we end up with for T2. Okay. Now, let's look at the other path. Okay. So in that case, we have the splitter to M1, and the ether drag is this way, okay? Now, the idea here is kind of similar to a swimmer going across a river, all right? So let's say that you're on one bank of a river and you're trying to swim across to the other bank of the river. So here's the river, right? Here's the bank where you want to be. Here you are. Now, the river is traveling with a speed. Let's say that the speed V of the river, the water is flowing like that, okay? If you just jump in the river and try to swim straight forward, the river will actually carry you downstream, right? So your trajectory would then be to the left and you'd miss your spot. Okay, so that's not what you want to do. So if you want to travel straight, what you've got to do is swim kind of at an angle, and then when you swim kind of at an angle, you'll reach the other bank on the opposite side at the point that you want, which is straight across from you. So this is the idea of what was happening with the ether drag, okay? It wasn't missing the mirror, okay? So that must mean that it had a little angular component going to the side, all right? So the path of the light actually looked kind of like this. It was at a slight angle, okay? And then here was the ether drag vector like that. And those two things were oriented so that they would be perpendicular to each other. So this is supposed to be a right triangle, even though I'm not a great artist, okay? So that would make the effective speed of the light as it crossed this leg of the triangle here. So C is the hypotenuse of this vector addition, right? C is the hypotenuse, and V is the vector that points left. So this other straight edge, not the hypotenuse, but one of the regular sides of the triangle, would then have a length of the square root of C squared minus V squared. So the light speed would be the square root of C squared minus V squared across from the splitter to M1. Okay, so that's the speed of the light as it crosses there. Okay, so that's what we've got going on there. Now, this would be the same magnitude speed. V would change direction as it comes back. V would change direction, but that wouldn't change the fact that the effective speed would still be this leg of the triangle. So even though the triangle would flip across the up and down axis according to this paper, even though it would flip like that, that still means that the effective speed is the same as from going from the splitter to mirror one and then back again. It's the same speed. So that means that T1, which is the time that it takes to go from the splitter to M1 and back again, would be equal to, yet again, the distance divided by the time. So that's L1 over the square root of c squared minus v squared, but it traverses that path twice, so you just multiply that times 2. Okay, so that's the amount of time that it takes to get from the splitter to M1 and back again. Okay, now what creates the interference fringes is if these two things are out of sync, there's a little interference pattern that's created. And so what we want to do is compare the amount of time that it takes for one path versus the other path. And to do that, we need to subtract T2 from T1. Okay, so we're going to take these two equations for T2 and T1 that I just derived and subtract them. Okay, and that's our next step. And that'll become our delta T. So let's go ahead and do that. So here we have delta T will be equal to T2 minus T1, and this is the time difference between light paths. Okay. And then that delta T will be equal to T2 was 2L2C over C squared minus V squared. And then T1 was 2L1 over the square root of C squared minus V squared. Okay. All right, so that's our delta T. And now that's our result for when the ether drag is along L2, when L2 is parallel to the ether drag. Now we're going to do the other case where we have the L1 parallel to the ether drag. Now, of course, this is going to be basically exactly the same derivation. Okay, it's going to be exactly the same derivation. There's no reason that it would really be any different. Okay, so the delta T prime, all right, is when the ether drag is oriented this way. So now here's our ether drag like this. Here's M1 and here's M2. Okay, so now the ether drag is pointing parallel to path L1 instead of path L2. That doesn't really change too much. So you'll see what I mean. What happens here is delta T prime is T2 prime minus T1 prime. Okay. And so here's what it does. It just says, okay, now it's our path 2 that has to do that weird little perpendicular thing with the C and the V, right? And so that's 2L2 over the square root of C squared minus V squared. Okay, because now path 2 is the one that's perpendicular to the ether drag. And then we're going to have path 1 be the one that is parallel to the ether drag. Okay, so that's our delta T prime. So what they were doing is they were looking for the difference in between the two different paths. So if you want to see if two time differences are the same, then you should just subtract them again. So here we have delta T minus delta T prime would show the differences of the ether drag being in different directions. If there is an ether, then it shouldn't be the same. But if there's not an ether, then it, really should be the same, and we'll show that. Okay? All right, so let's do the math. We have these two equations. It's relatively straightforward algebra. It's not always fun to do relatively straightforward algebra, but it's very doable. So let's do our delta T minus delta T prime and see what we get. Okay, so delta T minus delta T prime is equal to 2L2C over C squared minus V squared minus 2L1 over the square root of C squared minus V squared. And then we're subtracting off delta T prime, which is 2L2 over the square root of C squared minus V squared minus 2L1C over C squared minus V squared. Okay. Okay, so first of all, there's a little trick that that I'm going to do, and it's because I know that the Taylor series expansion is coming, okay? I know it's coming. So I'm going to go ahead and do part of the work now. So first of all, there's a 2 everywhere. I can pull that out, right? And second of all, I can pull out a C from the whole thing as well. Now, when I pull out 2 over C, here's what happens, okay? Let's do this here. So we have L2. Now, look what happens here. If I pull out the 2, there's my L2, right? I have a C on top and a C squared on the bottom. If what happens is I factor out a C from the top, then I just have C squared minus V squared here on the bottom. Well, actually, let me just show you in this one step so I don't confuse the heck out of everybody. Okay, so focus in. So here I have 2L2C over C squared minus V squared. That's equal to 2L2C over, I'm going to factor out a C squared, and that's 1 minus V squared over C squared. And then that would be equal to, one of this cancels out, C, right? So then that's 2 over C times L2 over 1 minus V squared over C squared. Okay, so that's what happens. So now going back, I'm going to plug that in and show you what else happens. So here you have delta t minus delta t prime. And then that gives me, here we have our pulling 2 over c out from everything. We have L2 over 1 minus v squared over c squared. That gives us one term. Okay. Now, I'm going to do the same factoring out with this second term, 2L1 over the square root of c squared minus v squared. All right. If I do that, then what would happen here is, to focus in, you have 2L1 over C over the square root of C squared minus V squared, like that. Or, I'm sorry, 1 minus V squared over C squared. Bad, Tanya, no biscuit. It becomes a C when it moves outside of the square root, right? Because you're taking the square root of it. So then that factors out. So then this becomes minus L1 over the square root of 1 minus V squared over C squared here, because you see the 2 over C is out front. Now here I'm going to have the same thing here, minus L2 over the square root of 1 minus V squared over C squared here. Okay. And then this guy, this last term, is the same as the first term. It's just got an L1 in it, and you have a minus, so it's a plus. L1 over 1 minus V squared over C squared. Okay. All right. So now what we can do, just to help our eyes a little bit, is group terms of L2 and L1. So here I'm going to have, this is equal to 2 over C, and then here I've got L2, and then L2 has 1 over 1 minus V squared over C squared for the plus, and then for the minus, 1 over the square root of 1 minus V squared over C squared. And then for L1, I have plus L1, and it gives me the same thing, 1 over 1 minus V squared over C squared minus 1 over the square root of 1 minus V squared. Come on, pen, over C squared. Okay. Okay, well, the first thing I think when I look at this equation is, well, gee whiz, if V is equal to 0, then this is 0. Right? Because if V is equal to 0, then all of these things here, 1 over 1 minus V squared over C squared, it becomes 1 over 1 minus 0, right? Same thing for this second one. It becomes 1 over the square root of 1, which is just 1. And then I have 1 minus 1, and that's 0. And then I get the same thing for the stuff multiplying L1. It's just 0. So if there is no ether drag, if V is equal to 0, then those time differences are the same, basically, and there is no delta T difference, okay? So no ether. Okay, so that's what we're doing there. All right, but let's pretend for a second that there is an ether and put ourselves in the position of Michelson and Morley at that point. All right, Now, everybody knew that the speed of the Earth through its in its orbit around the sun would be a nice estimate for the at least to first order for the speed of the Earth through the ether. Okay, if the ether is truly the ultimate reference frame and everything is moving with respect to it, which we know the Earth is, then that would be at least one approximation to that speed. And they knew the speed of the Earth in its orbit, and that's at about 3 times 10 to the 4th meters per second or so. Now, it might be different, you know, like our motion through space might change things or whatever, but that's a nice place to start. Now, we also know that the speed of light is 3 times 10 to the 8th meters per second or so. So we know that v is much, much less than c. Okay, our speed through the ether is going to be a lot less than the speed of light. And so that's why we can use those Taylor series approximations that we're going to use here in a second, because we know that v squared over c squared is therefore going to be much, much less than 1. So we can use those approximations when looking at this subtraction to place lower limits on things. Okay? All right. So let's do this. What are these Taylor series approximations that I'm going to use? Okay, so the Taylor series that I will use are that 1 minus x to the minus 1 power is approximately equal to 1 plus x squared plus dot, 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 4x a lot less than 1, right? And the other one that I'm going to use is 1 minus x to the minus 1/2 power is approximately equal to 1 plus 1/2 x plus 1 times 3 over 2 times 4x squared plus dot, 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 4x less than 1. Okay? Now, because x is much, much less than 1, I'm only going to keep first order. And that should be enough. So I'm going to truncate it right here in my approximations. Okay, so if I do that, then x is v squared over c squared. And so 1 over 1 minus v squared over c squared, I can say is approximately equal to 1 plus, let's see, where did it go? Yeah, 1 plus v squared over c squared. And then 1 over the square root of 1 minus v squared over c squared is going to be approximately equal to 1 plus 1/2 v squared over c squared. All right. So now, if we take these approximations and plug them in to our equation here for delta t minus delta t prime, everywhere I see a 1 over 1 minus v squared over c squared, I'm going to plug in that approximation. Everywhere I see a 1 over the square root of 1 minus v squared or c squared, I'm going to plug in that approximation. Okay, so let's do that. So then delta t minus delta t prime is going to be approximately equal to 2 over c times L2 times 1/2 v squared over c squared plus L1 times 1/2 v squared over c squared. Okay? All right. And that's because if you subtract these two things right here, if you subtract them, which you do in the equations for L1 and L2 and the time differences, if you subtract 1 plus v squared over c squared minus 1 plus 1/2 v squared over c squared, then you get 1/2 v squared over c squared for each one. Okay, so that's what they got. So now this bit here is equal to, the 2's cancel with the 1/2's on the inside, so we end up with L1 plus L2, grouping terms, times v squared over c cubed. And that would be our delta t minus delta t prime equation. Okay, and this is the one that you'll see in your book. So now let's talk turkey. So this is the Michelson-Morley equation here. And let's talk turkey. We've already talked about what v and c are. or at least what, the approximations are, 3 times 10 to the 4th meters per second for V, and 3 times 10 to the 8th meters per second for C squared. In the final Michelson and Morley apparatus, L1 and L2 were about 11 meters. That was the path length, okay? So let's plug in for that. V is equal to 3 times 10 to the 4th meters per second. C is equal to 3 times 10 to the 8th meters per second, and 11 meters, and figure out what delta t minus delta t prime would be. That's going to be 22 meters times 3 times 10 to the 4th meters per second quantity squared over 3 times 10 to the 8th meters per second quantity cubed. And that gives me 7.3 times 10 to the minus 16 seconds. Okay. So that was kind of the sensitivity or what they expected to get. That was what they expected to get for the time shift for their apparatus between the two beam paths. Now, it doesn't seem like a lot. And so, especially in the time period in which they lived, you might say, well, gosh, is that even possible? Was that even possible during that time period? And the answer is yes. So in the final apparatus, they actually had these things floating on a pool of liquid mercury to baffle out vibrations and things like that to affect the sensitivity. And so they were able to actually get the sensitivity low enough that they could see that difference and even slower ether speeds. Okay, so let's put numbers on this. Let's say that C is equal to lambda F, right? Of course, that's the equation linking the speed of light to the wavelength and frequency of light. And let's take 600 nanometers as the wavelength of the light, which is red light. So this is red. And then let's look at what the time would be here for that. So if you solve, then you get a frequency of 5 times 10 to the 14th hertz. That would be the frequency of the light. And then the period is equal to 1 over the frequency. So if you solve for the period, then you get a time of 2 times 10 to the minus 15 seconds. Okay. So if you compare that to what they expected to see, this is the time shift for a full wavelength. Now they could see partial wavelength shifts in there. Okay, they could see partial wavelength shifts, and they could see as much as 0.005 wavelength shifts. So that was possible with their apparatus. Okay, and so let's multiply 0.005 wavelength shifts times that 2 times 10 to the minus 15 seconds. And you can see that that's 1 times 10 to the minus 17 seconds. Okay, so if this is what's possible, that's what was possible. And then let's look at what they anticipated. What they anticipated was 7.3 times 10 to the minus 16 seconds. Okay. Okay, so they should be able to see that. But the fact was that they didn't see any frequency, or they didn't see any fringe shift at all. So they saw no shifting of the fringes. So that would mean basically that the speed was so low, our speed through the ether was so low that it was not detectable with the device that they had built. So let's compare what was possible now and see what ether speed that corresponds to. Okay, so what ether speed corresponds to the sensitivity of the device? That's the floor. Okay, so here we have v squared over c cubed times 22 meters. And then the sensitivity of the device was 1 times 10 to the minus 17 seconds. And then if you solve that, you get v is about 3,500 meters per second. Now, since the speed of the Earth through the ether was assumed to be at least the orbital speed of the Earth, least 3 times 10 to the 4 meters per second, this seemed really unlikely. And so that's the null result. Okay, so that's the null result that Michelson and Morley got, and that's how they disproved the existence of the ether. Okay, well, I hope that you understood and followed that delve into the luminiferous ether. I hope you get it and enjoyed it, and I'll see you next time, okay?